How'd everyone find the test? Good. Got some thumbs up and some people looking away. Yeah, okay, it happens. So if you did not do as well as you had hoped, it's only 15%, so there's definitely room for improvement. The other 3 remaining tests will all have the same formatting, so if you did well, just keep doing what you're doing. If you didn't do so well, you're always welcome, of course, to come to office hours or email me or ask questions in course questions. I do want to help, but you do have to put in the work as well. So someone was asking if today's class would be fun enough to justify you all missing the beautiful weather. That's, let's call it very open to debate. So the first half of today is going to be on Appendix B. This used to be part of the body of the textbook. I think it was part of chapter 14 before, but now it's an appendix. But it's still, I think, really important to know about. Towards the end of the chapter, it'll become sort of clear why it was moved to the back, but we'll get to that later. This is the only time we'll go out of order. After this, we'll do chapter 5 for the second half or third of class, and then after that, we just go in order straight to chapter 15 for the rest of the semester. I'll remind you of this at the end of class as well, but I'll just say it again at the beginning. Next week is data day. So next week, your survey must be finished. And you should be here, as I like to say, unless you get hit by a bus. So unless you have a really good excuse, you should be here next week for data day. We will all do the surveys, everyone except me, and then we'll analyze the data, and I'll show you how to put that into your research paper. Yes?
When we save ours, is there a certain file name you want us to save it under? Because there's 3 with my name on it, and I don't know why.
You mean in the Qualtrics?
Yeah.
It doesn't matter. Just make sure you know which one's the right one. And just speaking of saving, make sure you either bring a USB stick or remember to email yourself the files at the end. Because if you save it onto the computer and log out, you lose it.
I was just wondering where else we can work on it other than the computer.
Sorry?
Where else can we work on it, like the Qualtrics one?
So Qualtrics you can do on any computer. It's SPSS you need these computers for. Now, it's a pain in the ass to log into Qualtrics, as we saw. So if you have trouble, just send me an email. But just to remind you all, basically, you have to either delete your history or use a browser that isn't logged in with Douglas. Because if you're logged into your Douglas account, it'll conflict with using the special Qualtrics login. So that's the key thing. But you can do that on any computer. It doesn't have to be this. Now, for the statistical software, like SPSS or Super Excel, basically, that you need these computers, unless you want to spend money. Any other questions, since it's very important? Yeah, okay. So let's get started on Appendix B. Appendix B is on inferential statistics, most of it being about one specific kind of inferential statistics. But first, let's say what that is. So there are, broadly speaking, 2 types of statistics, descriptive and inferential. So descriptive comes from the word describe. So you are describing what you found or summarizing what you found. You have your data. If someone asks you to summarize what's in there, one thing to do is to read every cell in the data set. But that's useless, so you have various ways of condensing the information. So things like the mean, right? You're saying what the average score is for some variable. The standard deviation or other measures of variability. Something like the correlation coefficient would also count as a descriptive statistic. You're describing the relationship between 2 variables in the data set. that's descriptive statistics. Inferential statistics are about drawing an inference from your sample to the population. When you get your sample and run your descriptive statistics, like the mean, the median, or standard deviation, the hard truth is no one cares about your sample, right? 100 people you got into the lab and gave the questions, those people don't really matter. What you care about is what inference you can draw about the population. So we saw one inferential statistic last class, so the class before the test, which is confidence intervals. That's one example of an inferential statistic. The number is about how confident you are that the population value is in a certain range. So in your sample, I think the example I used was 42% of people say they're going to vote for the Liberals, and let's say you're 95% sure it's within plus or minus 3%. That means you're 95% confident that the population value is between 39 and 45. So that's an example of an inferential statistic. Any questions about the basic difference? So today, we're going to be spending most of our time talking about one specific kind of inferential statistics, which is null, hypothesis, significance testing, or NHST. So this is a very widely used method in especially the social and biological sciences. So in psychology, it's ubiquitous, it's everywhere. As we will see, some people think it should be used less. There's various issues that come up here. Just as a funny note, a very important statistician named Cohen said that it should be called statistical hypothesis inference testing, or this. So that's Cohen's opinion. Statistical hypothesis inference testing. So it is a controversial subject, but so far the critics are not winning. NHST is still very widely used in psychology, medicine, the other social sciences. And so it's important to know how it works and to know about its limitations. So what is null hypothesis significance testing? Well, let's start with what the null hypothesis is. I'll have it up top. So the null hypothesis is the hypothesis you want to be false. You want to reject this. In the social sciences and the biological sciences, it is almost always the hypothesis of no effect or no correlation. So you want to reject that. You want to conclude, no, there actually is an effect or a correlation. It is sometimes called HO, H0. And this may help you remember, another professor here, when I took a similar class, said, you want to reject the hoe. So there you go, that helps. When I was in that class, the guy beside me was like, boys, let's talk about some hoes in our life we have to reject. So there you go, that helps. That's the null hypothesis. So to use the simple survey example that I gave you as the template, In the case of a correlation, it would be the hypothesis that the correlation between happiness and self-esteem, or whatever it was, is 0. Right, that would be one. That's an example of a null hypothesis. And then H1, which really matters less as far as how null hypothesis significance testing is actually used. H1 is a hypothesis that there is an effect, which is kind of weak as far as a hypothesis goes. In more rigorous areas of science, you're able to derive a specific prediction, right? That the effect will be exactly this size. Theories in psychology are typically not well developed enough to give you more specific predictions. Often you just say, I predict there will be a correlation. Or maybe at least I can predict there will be a positive correlation. It'll be in this direction. That's still pretty weak. So here's what we do. We assume the null is true and figure out what would follow from that. More specifically, we calculate something called, and this is, let me see if I have it better. Oh wow, that's much worse. We calculate something called a p-value. This is the most important number for understanding how this procedure works. Here, if you forget everything else in this class, remember the p-value. I'm going to give you the short version. I could add some stuff, and I'll mention it in passing later, but here's the core thing to hold in your mind when using this procedure. The p-value is the probability of getting your result if the null hypothesis is true. It's the probability of getting your result if the null hypothesis is true. So that's, yeah.
You want to reject the null hypothesis.
Yes.
But you are also wanting it to be true?
No, so when I said assume it's true, I mean like, if it was true, what follows from that?
Okay.
And I'll make that more concrete with the example I'm going to use. Because that all sounded, I'm sure, very abstract, but let's make it concrete. Let's say you're looking for a sex difference. This is the example I use in intro. So here's the population. There's men and women. Let's say that you're looking for a sex difference in video game playing hours per week. So the null hypothesis would be men and women play exactly the same amount of video games per week. So there's no difference in video game playing between men and women. You can't ask everyone, and let's say we're talking about Canadian males and females. You can't ask everyone, that's too hard, so you get a sample. So let's say we get 1,000 men and 1,000 women in our sample, and we ask them, how many hours of video games do you play per week? The men say, let's say 10 hours, and the women say 1 hour. So that's the number you get. So here's the key thing. It's possible that in the population, the null hypothesis is true, that there's no difference in video game playing behavior. And you got this just through sampling error. You sort of got unlucky. You happened to sample more men that like video games, or more women who don't like video games. So in this context, the p-value, actually forget about the p-value for a second. Forget about math and statistics. Just think intuitively, if the null is true, how likely is it we would get this? Is it
0?
not 0, but low? Yeah, so intuitively like 0. But now it's never going to be actually 0, but it would be very low. Like you'd be very surprised if you got this result if in the population there's no difference. So yeah, so in this case, the p-value, and you have to know more information, but maybe 0.0001 or something. You have to know more information, but it would be very low. So in most cases, you want big numbers, like with correlations or with effect size. The p-value, you want it to be small. Smaller the better. Because if it's smaller, that means it's less likely you would get this if there's no effect. How are we doing so far? Good? Yes?
Could it also be said that the p-value is the value that you would assign to your result, supposing that you didn't get the result just merely by chance?
It's often summarized that way. Statisticians will complain about that way of putting it, but it's an okay heuristic. So often it's stated as, in some textbooks it'll say, the probability you would get these results by chance. It wouldn't pass muster in a statistics class, but it's maybe a useful heuristic. Okay, so that's the p-value. Now, a related term, which sounds really scary, but it's very simple, statistically significant, or statistical significance. Statistically significant just means, can anyone tell me from 2300 or intro? Yep.
P-value less than 0.05.
Yep, wait, p-value less than 0.05, or whatever your cutoff was. You can set different ones. Some people set a lower cutoff, but 0.05 in psychology, medicine is kind of the conventional one. And it's not as though God came down and said, thou must use 0.05. It's sort of arbitrary, but yes, it means the p-value is less than the cutoff, which is typically 0.05. Which is basically a way of saying we want it to be less than 5% likely that we would get this result if the null is true.
I have a question.
Yep.
So this is assuming that our sample is completely randomized to the population, right?
Yes.
Is there any way of calculating p-value with any of the other ways that we select samples?
This is a great question. So, yes, this is absolutely correct. This assumes random sampling. And then you may say, wait, but in psychology, we don't often use random sampling. The answer to which is yes. This is a problem. So it's, you should put less confidence in the p-value, given that one of the assumptions that led you to calculate this, we know to be false, namely, the sample's not random. So one professor I had he would give a longer, more precise definition of the p-value, and one thing he would include is that your assumptions are correct. Just to give you, to help your intuitions along, so this is an example of a pre-existing difference in the population. You could run the same thing with, whether a drug works. I do this with my intro students to help their intuitions along. In that case, the null hypothesis would be the drug doesn't work. So if you had a case where you have the placebo group and the real drug group, and the real drug group is way happier or has way less cancer or whatever it is, the p-value would correspond to how likely it is that you would get that difference if the drug doesn't work. Okay. One thing I'll note in passing before going to the next section, one thing that critics of null hypothesis significance testing often say is it's a little strange that we're testing the idea that the correlation or the effect is zero. What people will often say, and I believe Cohen said this, it's never exactly zero. in realistic situations, the null is going to be is always going to be false. You know, you can show this with big samples. People have tried testing this. If you get a big enough sample, even nonsense variables will be correlated more than 0. So that's something that I just wanted to flag. I won't test you on that, but it is a point that critics of this procedure often point out. Okay, so sampling distribution. Now I'm going to be a little bit loose here. I just want you to have the kind of intuition of what this is. In 2300, they're going to be more rigorous with it, but this will be good enough for our purposes. A sampling distribution, when you're making one, you assume the null is true, or say, if the null is true, this is what would happen. And you also keep in mind what the sample size is. So let's think of the, let's say your sample is 1,000, or I guess 2,000, because it's 1,000 men and 1,000 women in my example. So what this is it's all possible effects that you could get with a sample this big. So here's your population, and you imagine all different combinations of people that you could get with a sample of 2,000. In fact, rather than the sex difference case, let's think about a correlation case. Let's say you're looking at the correlation between happiness and self-esteem. So everyone in this population would have some value for happiness and for self-esteem. So the correlations can range from -1 to 1, 0 in the middle. So let's assume that in the population it's the correlation is 0. And then there's all possible combinations you can have of those people with samples of 2,000. These are all of the correlations you can get. And in fact, with a big sample, it'll be more narrow. So most of the values will be close to 0. So how do we get the p-value from this? Well, let's say the correlation you find is 0.7. What you do is you get the area under the curve past 0.7. So and you do that actually using calculus, which we will of course not do in this class. You get the computer to do that part. So you get the area under the curve. So what you get then is the probability of getting that correlation or something bigger. So the probability you get this or something more extreme, that's the p-value. So I see some, yeah.
Just to be clear, the x-axis represents the mean difference.
Mean difference, or in this case, the correlation. I decided to use a correlation example. I thought that would be more helpful. But it would be a mean difference if it was like a sex difference case or a experiment. Yeah. So, like I said, I'm not going to be too picky with this. In fact, I'll go ahead and say sampling distribution is not on the test. This is just to give you an intuitive sense of how one gets the p-value. So one thing that's come up when we're using SPSS is one-tailed versus two-tailed tests. So the area under the curve is what gives you that probability number, right? The p-value. So this would be a one-tailed, like the way I just drew it here. Two-tailed means you're looking at both sides. So if your cutoff is 0.05, if you're doing one-tailed, this area needs to be 0.05. If it's two-tailed, it'll be a little bit less, and then you have to have both. Area under the curve in both directions. Here's all I want you to know, though, as far as one versus two-tailed. Again, I'll tell you, that's not on the test, but when doing your analyses, and in general when you're doing research, in my view, the honest way to go about it is you use a one-tailed test only if you made a directional prediction. In other words, you said in advance, I predict that the correlation will be positive, or I predict this group will have a higher score than this group. If you make no prediction about which way the effect will go, then you should use a two-tailed test. Okay. So I've been using the term cutoff that, in psychology and related fields, we use the cutoff, 0.05. The fancy term, yes?
Would we still use these types of prediction or one to two-tailed if we predict the null hypothesis?
If you're predicting the null, actually, yeah, then you would just use a two-tailed test. Yeah. Although I'll say, yeah, it's more interesting if you predict something directional. Anyways, yeah, so alpha is the fancy term for the cutoff. So the value you say that you want the p-value to be under. So as I've already said, in most cases, alpha is 0.05. Yep.
In 2300, the alpha was referred to as the actual t-test or t-score value.
So the t-score value that you get, so it'll be under 0.05. What that means is this is the t-value you need for the p-value to be less than. Yeah.
So in this course, it's just the p-value.
In this course, you'll put the t number.
But we're not worried about t-crit.
Yeah, don't worry about t-crit. Worry about it in 2300. What I really want you to have in your head is to be able to have an intuition about what the p-value is. And it's easier to get one. There is an intuition you can get about what t-crit means and what the t-value is, but the p-value is nice because the logic is the same whether it's an f-test, a t-test. Exactly. So that's more what I want to get across. In 2300, you suffer through learning all these different tests. So I believe in reducing suffering. So.
Okay, cool.
So speaking of the t-test, so as I say, in 2300, you'll learn about different kinds of t-tests. In this class, we're only focused on one. In other classes, you will, as I say, be made to suffer. We'll be using the t-test for comparing two different groups. So if you took 2300, this is the independent samples t-test. So the t-test is used for, in this class, when you have your sample, so in our case, your 30 people, randomly assigned to two groups, and you're looking for a difference between the two groups. And you want to decide whether that difference is significant. So let's say, and obviously we won't do this in your surveys, but let's say one group gets, cognitive behavioral therapy, and the other group gets a placebo pill. And you compare how happy they are on a scale of 1 to 7. It's kind of a simplistic way of doing it, but let's say this group is 6 out of 7, this group is 2 out of 7. So without getting into the actual numbers, conceptually, as the book says, the t-value is equivalent to the group difference, so how different these two are, divided by the amount of within group variability. So if we took 2300, that should ring some bells. Although you would have used numbers. And the idea is you want the top thing to be bigger. So the difference between these two groups to be bigger. And the amount of variability within each group to be smaller. Both of those will make t bigger. And here, t we want to be big. So there's different ways of making that intuitive. So let's focus on this CBT and placebo case. So we're looking at happiness scores. We want to see if CBT makes people happier. So here's two cases. Let's say it looks like this. So here's one way the effects could look. So these are two curves. So the CBT group, the curve is higher up, so they're on average happier. I'll make it really extreme. So in this case, the group difference is larger, right? The amount of within group variability is basically the same. I tried to make those distributions roughly the same shape. You don't have to be a statistician to know. You'd be more confident this one is a real difference, right? This would get you a lower p-value, right? Higher t-value means lower p-value. Is that intuitive? Does that first part make sense? Yeah, so obviously, bigger group difference is better. Now, the next bit is not as obvious at first, but when you see it visually, it's clear. So let's say there's a case like this. So here's the placebo group, here's the CBT group. So there's a modest difference between them in terms of the raw score, but the distributions are very wide. So there's a lot of within-group variability. Each group has a wide range, or a big standard deviation. And now I'm going to try and make the difference the same. So imagine instead it looked like this. The same, difference. Like let's say this corresponds to 4 out of 7 versus 5 out of 7. So not a super big number. But if each distribution is really skinny, so to speak, so really low within group variability, like which result would make you more confident in CBT? The second one, right? That looks more like a real difference between these two groups. Because when there's more within group variability, there's more overlap between the two groups. Any questions about that? Yep.
So within group variability, just from my own brain here, is essentially just another word for standard deviation, correct?
Or standard deviation would be one way of measuring it. In the t-test, it won't be a standard deviation here. It's standard error, I'm 99% sure. But yes, if you want to use that as a heuristic, that's fine.
Okay.
So here's one final thing I'll say about this. So as I say, we want this to be bigger than this. This relates to another way of getting at what the null hypothesis is. One way of stating what the null hypothesis is it's saying that the reason for the group difference is the same reason for the within group variability. Because here's the thing, even if, let's say there really is no effect, the null is true, your samples won't be exactly the same, right? They'll be somewhat different, almost certainly, your two groups. They won't have exactly the same mean. But if the null is true, the reason the two groups are different is just, people are just different. You happen to get more, happy people in one group. And that cause, people are different due to random stuff, is what makes the within group variability exist. And so one way of saying, or at least getting at what the null is you're saying the cause of the group difference is the same cause of the within group variability. So like if t is 1, that's bad. You want it to be not 1. You want it to be higher. Okay, here, I'm just going to double check that it is standard error, just so there's not me lying on the internet. Yes, it is the standard error. So, this would be the standard error if you're taking 2300, which includes, so it's right here. It's the standard deviation divided by the sample size square rooted. I'll delete that part out. That'll just confuse people, but for whatever it's worth. Okay. Okay, I have good news. So the next section is on the f-test. You can skip that. The logic is very similar to the logic of the t-test, but don't worry about it. So f-test will not be either in your study or on the test. So as is implied by the examples I've given already, you can also get a statistic, get a p-value from a correlation. So the book has a brief section there. There, the null hypothesis is that the correlation is 0. Okay. Next, we'll talk about the two types of errors. So you have 2300, or actually I think intro they talk about it too. You learned about type 1 and type 2 errors. So there's now a section on that. So you have to talk about two things first. There's the true state of the world, or the true state in the population. I think I jokingly referred to, like what God knows. Like that's here, right? So God knows whether your hypothesis is right or wrong. That's what this would be. But you are not God. Most religions would agree. Although I did have one professor who believed he was God. He was a panentheist, and he said that he knows that God exists because he knows that he is God. So there you go. I wish I had that kind of confidence. But, so you are not God. So you have a sample, you have limited information, and you make a decision about whether your hypothesis is true or not. So there's the null is true, null is false. So null is true means in the population there's no effect. Null is false means there is an effect. Then there's your decision, which you make with your limited information. And you either reject, actually this is not true. You reject, reject the null, or the book says accept the null. Some people who are more picky will say you really should say fail to reject the null, but we'll keep this because it's good enough for now. So in these two boxes, you're fine, right? So if you, quote, accept the null, so you say there's no effect, and in fact, the null is true, there is no effect. Okay, you made the right decision. If you rejected the null, so you say, actually, no, there is an effect here, and there is one, there is an effect, null is false, you're good. So let me make it concrete. Let's say that it's a drug. So you have an IQ pill. So null is false, or null is true would mean the pill does not work. The pill is garbage. That's the null. Null is false is the pill is not garbage. The pill actually does something. So these two boxes are where you get the two types of errors. Type 1 error, also called a false positive. So you rejected the null, so you concluded based on your sample that the IQ pill works. But in fact, the pill is shit. The null is true. It does not work. So the positive part, it doesn't mean positive or negative correlation, it just means there is an effect. And the false part corresponds to your decision. It doesn't make sense to say the world is false, or that doesn't mean anything. This part is about what's true in the world. This is about what you decided. So positive means you say there's an effect, but false means you made a mistake. And not a mistake like you did something wrong, it's just you reached the wrong conclusion based on the sample that you had. Type 2 error. Actually, first, does type 1 error make sense? Okay. Type 2 error, also called false negative. By the way, this is for free. If you want to remember which is which, you can use whatever you want. Here's the goofy thing I did. So type 2 is like with the Roman numerals. I imagined one of them rotating into a minus sign, so it's -1. That's what I did to remember. But you can do whatever works for you. So this should be clear what's coming next. So you accept the null, or fail to reject. So you conclude the drug doesn't work, but actually it does work. The null is false. Any questions? How are we doing? Are you guys just overwhelmed with excitement and interest?
Can you just explain the association between the left column and then there was one?
Yeah, so the left column, so you mean this, right?
Yeah.
So this is what you decide. So you guys will make decisions, so to speak, based on your sample when you do your survey. You will either, so basically, you'll reject the null if there's a p-value less than 0.05. And if it's not, then you'll accept or fail to reject the null. So now you make this decision based on a limited sample, so you could be right or wrong. It's just a decision you're coming to based on your sample. So if you reject the null, so you say that the pill works, but it actually doesn't work, then you're in this box. So again, if this helps, this is what God knows, so to speak, right? God knows, he looks at your pill, that pill doesn't do anything. The null is true. Null meaning null hypothesis. But you conclude based on your little sample that that the drug does work. So you've made a type 1 error. And then in this box, the null is false, so the pill does do something. But you conclude, nope, doesn't do anything. You accept the null. Yep.
You said that if the p-value is greater than 0.05, you're rejecting the null. Sorry, you're accepting the null.
Yeah,
Or
yes.
not.
Or failing to reject. Yeah.
But that doesn't necessarily mean that you concluded that the null hypothesis.
Yes,
Okay.
I was speaking a bit loosely there just to get the point across, but yes, that it's not the same as concluding that it's true. Just saying we don't have enough evidence to conclude it's false. If you're being more careful, that's what you're saying. Good question. Okay. Any last questions before I erase all this fun stuff? Okay, one thing, just as an aside, I discovered this recently. So some of you might find this interesting if you're a nerd. So as I mentioned, oh yeah.
I understand that whether the null hypothesis is true or false in God's view, whatever, but what are some indications of that? Because this concept is useless unless you can somehow indicate that
It relates to something that someone else asked. It is kind of theoretical. The answer is you don't really know. I mean, I guess one indication, this connects to what we're going to talk about in a bit, which is the replication crisis. One indication that you've made that mistake is if you find the effect and then a bunch of people replicate it and don't find it, which happens, which we'll talk about. Or at the now, I should be careful. At the very least, it indicates the effect is probably very small. The null still might be false in a technical sense because it's not literally zero, but at the very least, the effect is much smaller than you would have guessed. So again, this is typically used in the social and biological sciences, but I did discover it's occasionally used in physics. A context in which it's used in physics is particle detection. So the null in this case is there is only background fluctuation. So they get the particle accelerator, they smash things together, and then they do some math that I don't understand, but you can say what you would expect on the basis of background fluctuation, so no new particle, and then you look at the energy levels or whatever that you get, and you say, how likely is it that I would get this if there's no new particle, which would be the null. Now, one thing that's interesting about this, so in psychology, medicine, etc., the cutoff is 0.05. In physics, it is 0.603. So, because physics, they're more serious. You know, they're very picky about what counts as good evidence. So, this is a reflection of that. This is called the 5 sigma cutoff, whereas we use a 2 sigma cutoff. But this is not testable. I see some people who seem like this was interesting, so this was for those 3 people. So, like for example, when they detected the Higgs boson, this is what they used. Okay, so we're over the most difficult parts of this chapter. Now I'm going to use this to lead into a discussion of the replication crisis, which is very important, and it connects with some of the things that we've been talking about. Although, since the hardest part's over, maybe that's a good place for a break. Let's take a break here. Come back at 4:35. How's everybody feeling? Anybody have a headache? NHST? No? Headache free? Okay, good. So as I say, I'm going to use this as a chance to talk about the replication crisis. So just as kind of an interesting anecdote, when I took this class, I took it from Brian Nadeau, actually someone who sadly just passed away about a week ago. But when I took that class with him, someone asked, can we use an older edition of the textbook? And he said, well, there hasn't been any revolution in psychology in the last 40 years, so it probably doesn't matter. That was true when he said that, It is not true now. The replication crisis is part of the reason why this section is now an appendix. So the replication crisis was kind of just beginning around the time Brian said that, and that was around 10 years ago now. Ooh, I don't like that. Okay, it was 3 years ago now. So there's different ways of telling the story of how the replication crisis happened, but what I'm going to do is a pretty conventional way. Although before explaining it, I just want to put in your head one term, which is maybe the most important for understanding the replication crisis. There are some related terms that I'll talk about in a while, but just to get this into your head. So I mentioned that the conventional cutoff or alpha value or alpha level is 0.05. What that means is if you get a result with a p-value of 0.07, you're probably not getting it published. And this creates a potentially bad incentive structure because if you get your data set and you do some data analysis, and you have some degree of freedom in terms of how you analyze the data. Basically, if you do a bunch of different analyses and control for some variables and then try it without controlling for those variables and various other things, you'll pick whichever result gets you a p-value of less than 0.05. And this is referred to as p-hacking. And it need not be fraudulent or dishonest. This can be someone who's acting in good faith. They get their statistics, get their data, and you know different types of analyses, so you explore your data. But if you keep doing that until you get the p-value less than 0.05, you are greatly increasing the chance that you will get a false positive. The way to think about it is, if you do enough analyses, eventually you'll get something with a p-value of less than 0.05. And then that's the result you publish. Well, now you've put something in the literature that may or may not be real. In fact, is less likely to be real. So
basically, continue doing it until you get.
Yes.
That's p-hacking?
That's p-hacking. And what you want means p less than 0.05. So how bad, now that's just one contribution. I mean, I'll just say in passing, another key term that's right here is publication bias. And you can get this even without p-hacking. This just refers to the fact that journals only publish positive results. Right? They only publish results with p-values less than 0.05. So let's say all of us decide to do the same experiment. And most of us don't get a significant result, but one of us does. And we all submit to a journal. Which one does the journal accept? The one positive one. But if it happens like that, we actually should bet that it's a false positive, given if it turns out like that. So that's another way in which you can get results that aren't replicable. Yeah.
There's now a journal called in support of the null hypothesis.
That's true, I've heard of this. So yeah, so now that's where to submit to. Now, even though you can get it published in places like that, doesn't look as impressive on your CV, is still the truth. And I don't want to totally trash this. I mean, this makes some sense. I mean, saying I didn't find anything is kind of boring to people hiring instructors. If you have a whole CV full of, I didn't find anything, no one cares. And in some sense, they're right not to care, but it has this bad side effect that you're more likely to publish results that are false positives. So, yep.
But if you've done a bunch of studies and never found anything, wouldn't that mean you're just a really good scientist?
You could make value judgments here. So maybe if you're a certain kind of Karl Popper person, you could say, well, yeah, science is about conjecture and refutation. So, I falsified my hypotheses. So maybe you could say from that perspective, it's good. Certainly, I would say such a person is likely honest, which I like. But, if I choose between that guy, well, let's put it this way. If I hold honesty constant, there's two scientists, they're both equally honest, which we can't always know, but let's assume, and one found a bunch of stuff, well, that is just more interesting. But now, to some extent, this is a value question. It's like, which do we care more about? Whatever is right or wrong, so we could have discussions about what matters more. The fact is, in the field, even today, positive results are more valued. And this is sort of a cost of that. Yeah?
Doesn't even a negative value, doesn't that still add something to the research because you're still confirming?
Yes, this relates to another question, which is a p-value that's not less than 0.05 isn't strong evidence that the null is true. That's kind of the paradox. The cutoff of 0.05 is if we have less than this, we're going to say that's good evidence that the null is false. But the reverse isn't necessarily, in fact, it just isn't true. To make it concrete, let's say your p-value is 0.07. So it's not less than 0.05, so it's a negative result. But you wouldn't say, well, now I'm very confident that there's no effect. That's the way to think of it. So these are all very good questions. But just to give you the story, kind of the story that builds up to the punchline, there were a few steps that led up to the replication crisis, but then there was a crescendo, or a bomb, if you like. And after the bomb happened, the field went through, a crisis. One kind of early warning flag was 2005. There was a paper with the title of something like most published research is false. Or I think it's most published research findings are false, or whatever, something like that. And this one was just based on a model. John Ioannidis built a model with some assumptions that people could question. And he estimated that over half of published studies are false positives, based on things like this, things like publication bias, p-hacking, etc. But that was just a model, so people kind of ignored it. One thing that made the hair stand up on researchers' necks a little more was in 2011, Daryl Bem, who's an interesting character. He's sort of like Freud, kind of a mad genius. Very creative, but a little bit crazy. Claimed to have good evidence of ESP, or extrasensory perception. The article was called Feeling the Future. So he claimed to have evidence that people could sense the future. P less than 0.05 with several studies. And just as a funny aside, this chapter's pretty dry. Just to give you something funny to know about Bem. Bem also had a theory called exotic becomes erotic. This was his explanation of how homosexuality develops. It's one of the funniest theories I've ever seen. The idea is whichever sex you think is more weird when you're a kid, or more exotic, that's the one you become attracted to when you hit puberty. So if you grow up and you're a boy and you think, well, I don't get the girls, man, they're just so different from me. And when you hit puberty, that's who you become attracted to. But if you think that, if you're a boy and you think, oh, the other boys, they're just so weird, then that's who you become attracted to. Now, I only have one piece of relevant evidence, which is I told this to my gay friend, just kind of like joking around, and he said, it was like an epiphany. He was like, that makes perfect sense. When I was in elementary school, I couldn't accept that males were even in the same species as me. So, one data point, but of course, not everybody. So, anyways, Bem's kind of a weird dude, is kind of my point here. But the paper that he published followed the standard norms of the field at the time, and it yielded statistically significant evidence of ESP. And psychologists pretty universally were like, that can't be right. Think back to what I said about pseudoscience. If a finding from a weaker field contradicts something in a more well-established field, we view it with suspicion. And if ESP is real, our theories in physics have to be completely revised. Now, maybe they do, but it's not going to be psych surveys that are going to tell the physicists to change their theories. So universally, psychologists are like, something has to be wrong here. But BEM, as I said, followed the standard kind of practices in the field at the time. Like p-hacking was very common. In fact, BEM basically wrote the manual on how to p-hack. It's still available. He didn't call it that, but that's basically what it is. I think it's called How to Write an Empirical Article or something like that. Okay, so one more early warning sign before the bomb. In the same year, there was a paper called False Positive Psychology. Now, the details of this story I won't test you on, but it's kind of an interesting story. In false positive psychology, researchers, again, using the standard practices in the field, using basically p-hacking, found statistically significant evidence that listening to the Beatles makes you younger, that's right. So it makes you younger. I don't mean feel younger, I mean it makes your age a smaller number. P less than 0.05. Now, even someone like BEM is going to be like, that can't happen, right? Listening to music does not reverse time. But again, they were using the standard practices. So all of these early warning signs were part of the reason why in 2015, the Open Science Foundation, I think that's the name of the group, the Open Science Foundation, or I'll just say OSF, did 100 replications of random articles in top psychology journals. So they just got top psychology journals, picked 100 random studies, and looked at the methods section and did exactly what the methods sections said. And their question was, how many of these will give us p-values less than 0.05 when we replicate it? Any guesses? Actually, do any of you know the number? If you know the number, don't say, but guess if you don't know.
How many they found were?
How many were significant? How many were successful replications?
Zero.
Oh, whoa, okay, no, it's not that bad. Jesus, okay. We got a problem, we're not that, whoa, 36, so 36%. So 36 of them successfully replicated. Now, some people, the other number was how many of them were in the 95% confidence interval. I think there was closer to 50, but either way, that's not great, right? No matter which cutoff you use, a majority did not successfully replicate. So this sent the field into a bit of a panic, because then when you look at any article, you don't know which half it's in, so you sort of don't know how seriously to take it. So there are various things that have been said in response to this, but just to sort of review part of this story and also add some other numbers from this study, I have a video. We'll watch kind of the first bit of it. So it goes into more detail after that, but so I'm going to add some terms now that are relevant here. So I mentioned the term p-hacking. A broader term that you'll see, including in, I think, one video I show on another class, is questionable research practices. So that's an umbrella for p-hacking and also some other stuff. So this is different from fraud, where you're just making up, if you're making up data or moving people into a different condition to get an effect, then that's just fraud. These are, although now, maybe we might increase the definition of what counts as fraud, given that we know how bad these are. But prior to the replication crisis, I believe most people who were doing this were doing so in good faith. They weren't, I think, trying to pull the wool over our eyes. So one type of questionable research practice, these are sometimes called QRPs for short, is p-hacking. And a term that relates, think of it this way, another way of phrasing p-hacking is it's taking advantage of researcher degrees of freedom. by researcher degrees of freedom, I mean, when you analyze your data, you have certain decisions you have to make. How many analyses should I run? Should I add a covariate or a moderator? And if you don't know what that means, don't worry about it. But basically, different things you can do with the data. One example that I think I list in the key terms is you have to make a decision about exclusion criteria. You have to decide who you're going to exclude from the data set. And almost always you have to exclude some people. Especially if it's a big sample, you'll get some wild stuff. So in my lab at the University of Alberta, now this is post-replication crisis, so we were more strict about this, but we would exclude people who did the survey too quickly or took too long. So, you know, I made the survey, I do it, it takes me 20 minutes or half an hour. If you take less than 5 minutes, okay, you're out. Like, you're obviously not taking it seriously, you're just clicking through to get credit. Sometimes you have a question like, you know, what are the colors on the Canadian flag? Multiple choice. If you get that wrong, you're out. Right? Same if you take too long. If you take over 2 hours, the manipulation probably isn't affecting you anymore, so again, we'll exclude you. But in the old days, researchers may play with this, right? You may say, really, if you took less than 10 minutes, you know, that's still too short. But again, if you're maybe really creatively p-hacking, you know, you may try different exclusion criteria and see which one gets you a p-value less than 0.05. And again, if you do this enough times, eventually your chances of getting that low p-value get pretty high. It's pretty likely you'll get at least one thing with a p-value less than 0.05. Another questionable research practice is called harking. Hark means hypothesizing after results are known. Hypothesizing after results are known. So this means when you write the paper, and let's say you found some result, maybe using p-hacking, you pretend that's what you were predicting all along. So you say, you do a bunch of stuff, you find one thing that's significant, and again, it could be done in bad faith, but it might not be. It might be that you sort of forgot why you initially did the study, you get used to that result, and then you write it up as if that's what you were hypothesizing. So again, that's a related questionable research practice. And by the way, this is more so just so you know what these terms mean when you see them discussed. Nudge, nudge, hint, hint, p-hacking is the one to worry about. Okay, last term for this section is the solution. I considered making you all do this for this class, but I thought, it's too much work. But if you do an honors thesis here, or definitely if you want something published, this is a good thing to know about. And that's, does anyone know the magic term? Well, I guess it's on the key terms. Pre-registration. Increasingly, and I think this is a very, very positive thing, pre-registration is required for publication in good journals in psychology. In fact, I'll say this. Now here some people might not like this. In fact, I know for sure some people wouldn't like this. Psychology has taken a lot of heat from the replication crisis, but there are related fields like neuroscience and medicine that still use a lot of the same questionable research practices, but this is not emphasized as much. I think that now, I don't want to hate on psychology, in many ways we are leading the way with emphasizing the solutions. So, I should say, what is pre-registration? This is where you, before you collect your data, you say in advance what you're going to analyze, what your exclusion criteria are. So basically you tie your own hands behind your back. and you say, this is what I'm predicting, this is how I'm going to test that prediction, etc. So it's a way of preventing you from doing p-hacking. So of course, that makes it harder, but then if you get a significant result, researchers will view that with more confidence. Now I should add, even if you pre-register, there's nothing stopping you from doing exploratory analysis after. That's fine, but you just have to admit, this is not what I was originally predicting, so take it with a grain of salt. And then maybe replicate that with a pre-registered prediction, right? The finding that you found through going on a fishing expedition, seeing if you could find any other patterns in the data. Okay, any questions about those terms? No. Especially if it's, look, how honest do I want to be? I want to be very honest. My own field, social psych, in some ways was hit the hardest with this. If I see a paper published before like 2010, 2015, I sort of think, yeah, maybe. You know, like, as far as whether it's a real effect or not, because it was extremely common. And social psychology is what I know best, but other areas too, you kind of have a little bit of a question mark there. Yeah.
Does that mean that a lot of theories in cognitive psychology sort of aren't well backed up?
So one funny thing, now I don't remember the details here, but in some of these big replication attempts, they've looked at the replicability per field. If I remember correctly, in fact, no, I'm quite sure, cognitive was higher than social. So there are differences between the different fields in terms of how replicable the results are. So you can double check like the exact numbers there, but it's somewhat variable. But I have seen genuine improvement. I mean, I can even see it in sort of the habits that people have now, the kind of habits of thinking, habits of doing research have genuinely improved. For sure that's true in social psych. Like, I can see kind of the difference.
What are you looking
Well, I just mean like researchers I know, like watching like how we go about doing things.
for? Okay. So watching the actual.
And watching it in practice, like in labs I've been in, but also, I mean, papers now will say it's pre-registered. Like if you look at papers after this crisis, so like in my dissertation, all of mine except for study 1 are pre-registered, and good journals will list that. I will say too, and maybe I'll edit this out, but a lot of professors engage in, have I used the term copium yet? It's such a good word. My intro psych students, apparently it's out of fashion now, but for a while the kids were saying copium or cope. How many of you have heard the term cope or copium? Okay, so still at least it's a little old now, yeah. But basically it means telling yourself a nice story to make yourself feel better. I'll say it, whatever. So some researchers, I think, don't want to face the fact that some of their work prior to this may not be replicable or real effects. And I remember I was asked a question about this in my candidacy defense when I was a PhD student, and I said some of the stuff I've been saying now about how important pre-registration is. And I had one prof get really mad at me about how insistent I was on it, and I heard from someone I knew that he went on a big rant about it in his class. He's like, oh, this PhD student said this, or whatever. And basically he was trying to downplay the importance of pre-registration, and in my opinion, that's a lot of copium. A way of telling yourself that, no, my work was still solid, even if maybe it's questionable. So maybe I'll edit that part out. But, yeah. Okay, so I find this topic very interesting. I'll show 2 other videos. One which is a video that actually is how I first learned about the replication crisis. It's about one specific finding that was very hard hit by the replication crisis, which is ego depletion. How many of you have heard of ego depletion? Okay, good. Maybe it got cut out of the textbooks. So, ego depletion is the idea that self-control is a limited resource. And if you use it, you sort of become tired, or your self-control becomes tired, and you're less able to exert it in future tasks. That's the basic idea. And I'll show a video about how this effect came to be questioned after the replication crisis. So I remember when I first saw this. It was sort of the first time I heard that this was going on. Okay, so it's a nice concrete example. So to wrap up this chapter, I'm going to show one other video. This is a nice way to wrap up because this is Brian Earp, who, by the way, how many of you are thinking about going into grad school for psychology? So if you want to become very depressed, just look up Brian Earp's CV on Google Scholar. The man is a publication machine. Like it depresses me immensely. He works actually in some of the same areas that I do. But anyways, so he talks both about the replication crisis and reviews some of the kind of logical issues we talked about related to null hypothesis significance testing. So it's a nice note to end on. And then we'll end this chapter on. After this, we'll do chapter 5, which should take less time. Okay, I'll stop there. He goes on, but I think, as I say, it's a good kind of review of some of the issues we've talked about. Okay, any questions before we move on to chapter 5? Okay. So there's a chance we don't finish chapter 5. If that happens, we can save some of it for next week because the chapters are a bit shorter, but still almost an hour, so I think we should be able to finish. So, first term in the chapter is variable. Nice and easy start. Lots of big words in the last chapter. So, variable is just, well, one way of saying it is, it's anything that can vary. Anything that can be different between people. So it can be a situation, a behavior, a trait, anything like that, as long as it can be different between people. And one way of saying what this chapter is about is it's about how variables relate to each other. And this is review. Broadly speaking, you can look for correlations between variables or causal relationships between variables. In a non-experimental study, so a correlational study, you're just measuring two or more variables and looking at how they relate to each other. Whereas if you're doing an experiment, you are manipulating one of the variables. You're doing something to one group that you're not doing to the other group. So you have these variables. Now, in psychology, one of the main difficulties we have is the variables we are interested in are difficult to define. We are interested in variables like intelligence, anxiety, happiness, and as you would have seen in intro, there are debates about how to define these variables. And if you want to see it, just get a bunch of random intro textbooks and look at how they define intelligence. You will find different definitions. So that's a bit of an issue. The solution in psychology is to give operational definitions. So we're interested in a variable like intelligence. What is intelligence? We'll disagree. You You could have a philosophical argument, if you like, about what intelligence is. But if you're doing a research paper, you have to give some definition that's measurable and precise. So, in psychology, of course, the convention is to operationalize it as an IQ score. So, you say, in this study, we are going to operationally define intelligence as your score on an IQ test. This is, of course, not the same thing as saying that IQ tests are perfect or without their issues, but we have to define it in terms of something precise and measurable. Broadly speaking, there are three types of variables. Situational variables. So kind of self-explanatory. So one example might be, you randomly assign people to two conditions. In one condition, the room is hot, and in one condition, the room is cold. That's an example of it's about the situation you're in, and it's different between the two groups. There are response variables, so that's a variable that relates to what the person does, how they react to the situation. So that can include behavior, it can include button pushing on a survey, like your variables will be. And lastly, participant variables. These are variables that already exist when the person comes into the lab. So things like gender, ethnic group, height, whatever. Those are all things that basically they're variables you can't randomly assign people to different conditions. Age, you can't randomly assign people to the old and young condition. Okay, there's then a section on confounding variables, or I should say any questions about operational definitions or different types of variables. That should mostly be reviewed, yeah?
Can you repeat the three different kinds of variables?
Yeah, for sure. So situational, response, and participant. They should be on the key terms. There. So it then talks about confounding variables, and it talks about them in the context of operational definitions. To the extent that it connects it to that, don't worry about that. We'll talk about something called measurement error in a later chapter, which is more what this is getting at. But I will talk about what confounding variables are in general, since it's here. So here's what here's what a confounding variable is in general. Sometimes it's just called a confound for short. It's a variable that you don't care about, but sad, you can't separate it from the variable you do care about. And three, it can explain, potentially, the results you want. So that's like the broad definition. Yep.
You might touch on this, but I was just wondering, because this question that happened about what's the difference between compound and third variable?
A third variable is a confounding variable, I guess, just in the context of a correlation, is what I think is the right thing to say. Now, one thing I'll say is, so this is the broad definition. I'm in a good mood, it's a beautiful day. This is on the test, it's one of the terms. But I'll give you the option, you can write this Or you can write what a confounding variable is in the context of an experiment, which is easier to write. So I'm going to say that next. So you can go either way. And as I said, I'm going to be nice. This one is on the test. So in the context of an experiment, or a study that claims to be an experiment, here's an example of a confounding variable in that context. This is an example I use in intro, if you've taken intro with me. Suppose I want to test whether which teaching method is better. I have two teaching methods. I want to see which one's better. And I try one on some kids in Edmonton that I teach. So teaching method A. And I try teaching method B with my Vancouver kids. And then I measure their grades. The kids who are exposed to teaching method A, the average is 85 in the class, and for method B, it's 62. And we'll say p-value less than 0.05. And so I conclude teaching method A caused these kids to get a better grade in the course. Someone tell me, what's the confounding variable in this study?
Maybe the professor had other shit to do in Vancouver and Edmonton sucks.
Oh, no, I'm saying it's me. Like, let's say I teach you both. Although you're sort of getting at it. Yeah?
The city that they're in.
Yeah, so the way I said the city that they're in, right? So let's say it's me teaching in both. So I guess, yeah, it could be me having like nothing else to do. So yeah, so city that they're in is a confounding variable. So, right, it could be that there's nothing to do in Edmonton. It could be that the Vancouver kids are really sad because they never see the sun, except for now, like, very rarely see the sun. So the shorter definition of confounding variable that is fine for the test is it's anything that's different between the two groups other than the independent variable. So anything that's different between the two groups other than the independent variable. You want it to be the case that the independent variable is the only difference between the two groups. That's why you do random assignment, right? You're trying to make it so that the two groups are the same, except for the thing that you do to one group and don't do to the other, which is the independent variable. So in this case, there is a difference, right, where they're from. So this is just that definition I gave is really a case of this. This is the more broad definition, but either one's fine for the test. Any questions on confounding variables? Yep.
I'm just trying to think. That seems like there could be a whole lot of confounding variables if you define it. Anything that is different that's other than the
Yes.
ID. So like whatever they ate that morning, what time they went to bed, but we wouldn't say that any of those things caused the results, would we?
Oh, it's possible, right? So what you're pointing at there is sort of participant confounding variables. What you hope is that random assignment kind of takes care of that. There should be roughly, on average, the same number of people who had bad breakfast, good breakfast, or whatever. But strictly speaking, anything like that could be something that caused the results. Now, this is another reason why replication is important. Presumably, if you do this over and over again with randomization, stuff like that should wash out. But if you're being really picky, yes, strictly speaking, those would be confounding variables. Tell them to eat breakfast, yeah. So this is, yeah, basically, the more stuff you do like that, the more experimental control you have. I mean, it might be kind of odd to tell them that, but yeah, I mean, it is something you could do if you're being picky. Okay, so now we'll talk a bit more about correlations. So broadly speaking, this chapter is about zooming into correlational and experimental methods, although future chapters will do that in some other ways. But focusing on correlations first, there are multiple types of correlations that you should know. Two of them you'll have already seen. But there are a couple others that we'll talk about. So the correlations that you are all exposed to in intro psych are both examples of linear correlations. And by linear, I mean the correlation is best approximated by a straight line. Probably in intro, the professor would have just said positive and negative, but strictly speaking, these are positive linear correlations and negative linear correlations. Linear meaning just having to do with a straight line. And oftentimes that's good enough for the kinds of results we get, but sometimes you get patterns that are not best approximated by a straight line. So just to briefly repeat what positive and negative mean. So positive, I like the way the intro text put it. This means more is more, right? As one variable goes up, the other tends to go up too. So, you know, hours of studying and GPA, right? On average, higher in one, higher in the other, with some variability. I don't know for sure, but maybe hours of video games and GPA plausibly negatively correlated. More of one, less in the other. So negative means more is less. As one variable goes up, the other tends to go down. Okay, so this should be a review, but any questions about that? Okay, another type of correlation you can get is something called a curvilinear correlation, or curvilinear relationship, which means sometimes more is more, but sometimes more is less. In other words, the direction of the correlation changes at some point. The textbook examples usually are like U-shaped curves. So you can get cases like this. So just some real examples here. Masculinization of the face and attractiveness in males is a curvilinear relationship. So, now of course, on average, different strokes for different folks, but if you give like straight women different types of male faces, you find that the most attractive are moderately masculine. So not masculine at all, on average unattractive, but too masculine, it's not quite this simple, but too masculine, and it starts to look kind of like a murderer. It's like too much. So that's one example. One that looks like this is age and happiness. The happiest times in life are the 20s and retirement, or old age. So happiness peaks in the 20s, goes down, so enjoy it while it's here. But then it gets better when you're old again too, again on average. Oh, you're in it down? Oh, okay, so you can verify this.
It's not our fault.
Yeah.
Did you say sometimes more is more, but sometimes more is less?
Yes.
Okay. You're
So,
right.
curvilinear broadly, sometimes more is more, sometimes more is less.
We need happy folks.
So positive linear, negative linear, and curvilinear, those are the three probably most common. I'll tell you right now, the next one I won't test you on, but just to be complete, you can also have other relationships that are none of the above. So they're not linear, they're not a straight line, but they're not these sort of U-shaped relationships. So for example, is more common maybe in medicine, you can have exponential relationships, right? So days since the outbreak of a disease and number of cases, right? Usually often looks like this. So that all that falls under the heading of just other nonlinear relationships, but I won't test you on that, but just so you're exposed to the fact that you can get other sorts of relationships. Okay, the next one, I'm not gonna ask you to understand how this would work statistically, but I just want you to have an intuitive sense of what this means. And that's a mediated relationship. Now, this is kind of sneaky because strictly speaking, it's correlational data, but it's presented in a way that the researcher is saying, nudge, nudge, think that it's causal, is basically what this is. So X is correlated with Y, and nudge, nudge, X causes Y. I can't come out and say it, but that's what I think. And there's some other variable, M, the mediating variable, that is correlated with both. And for theoretical reasons, I think that X causes Y by means of M, or through M. So that's what mediating means. It's like, it's the variable in the middle. This one affects this other one through the middle one, the mediating variable.
Is that like the same as the Z variable?
So like what letter you put on them sort of doesn't matter, although Z I think is usually in like the software where they slap letters on them, it has an M slapped on it. I think Z is sometimes used for something else, but the letters are just like placeholders, doesn't really matter which. Yeah.
So is this like that example where there's like high ice cream sales correlate with?
No, I wouldn't think of it in terms of that. I'll give an example that'll help. So let's say you find, and I presume this is true, that child abuse, I mean I have no idea, I'm just making this up, but let's say child abuse is correlated with divorce. Hey, at least we have temporal precedence, that's one part. So you find that correlation, and let's say that you have this theory that the reason child abuse leads to divorce, again, you're kind of assuming a causal relationship, is that child abuse gives you attachment problems. You have a different attachment style. And so you measure levels of insecure attachment. And you find that this is correlated with this, I'm simplifying, and this is correlated with this. So you'll treat this one as the mediating variable. So that's an intuitive example. That's all you have to know. There are statistical things associated with this, but we will ignore that. So, any questions on this before?
How would you word it, like?
Yeah, so if you want a one-sentence definition, the mediating variable is the one, let's put it like this. If there's a mediated relationship, it means you think that X causes Y through M, is one way of saying it, or causes it by means of M. Yeah.
So is this for both correlation and causation?
Yeah, so you can do this in experiments too, where you measure a mediator. But in either case, you are sort of subtly saying, nudge, nudge, we think it's causal, even if strictly speaking, you only have correlational data. Okay, so leaving aside that case, so you all know at this point that correlation does not imply causation. one question you may ask is, what's the point of doing correlational studies? And one answer is, it does give you the ability to make predictions. Even if you don't know, what the causal relationship is, or if there's a causal relationship, you can still use it to make predictions. And the stronger the correlation is, the more confident you can be in making those predictions. So one case that you're all familiar with, I talk about this in intro, is the correlation between high school GPA and college GPA. Right, there is a correlation. And colleges and universities use that information when guessing or predicting how well you're going to do in college, and therefore making admission decisions. Even though the correlation isn't perfect, it does allow you to make predictions. Here's another case that I've started using that will make this, I think, really visceral. Suppose that you have to choose a babysitter, and there is a correlation between an agreeableness scale. So agreeableness is a measure in personality psychology that basically is like how nice and polite are you. So you have this agreeableness scale, and let's say what you're using it to predict is how mean the people are to kids. So number, I don't know, you could imagine different operationalizations, but we'll just say some mean to kids measure. So let's imagine in one case, first let's say your babysitter has a high score on agreeableness, but there's two different states of affairs. So in both cases, there. In one case, the correlation's like this, and you know that the babysitter's here. In the other case, so lower means less mean to kids, looks like this. Oh, sorry. In which case are you happier? This correlation or this correlation? The first one. Yeah, so if this is the number you see in the study and you know they're here, you're much more confident that they're not going to be mean to your kid. And that has nothing to do with causation. It doesn't matter if the connection's causal or not. The point is you can make a prediction pretty confidently that the babysitter's unlikely to be mean to your kid. Yep.
Is that for the reduction of uncertainty?
Yes. So reduction of uncertainty meaning basically more confident in your predictions. Okay. So this will be a review from intro, but I teach this a little bit differently than some people do, at least in terms of how I organize it. Whenever you have a correlation between two variables, there are three possibilities that you should consider. This is one way of capturing the directionality issue and the third variable problem. So the three possibilities are A causes B, B causes A, or C, some variable that you didn't measure, causes A and B. So, I think the example I use in intro is, let's say like playing sports is correlated with extroversion positively. So it could be that playing sports causes you to be more extroverted, right? It could be that being extroverted,
being extroverted causes you to play more sports, right? You're outgoing, you like people, so you seek out more sports. Or it could be that some third variable that you didn't measure causes both A and B. Good. Yeah, so that's the example. Were you in my intro class?
No.
Oh, there you go. You stole my example without knowing it. So yes, one possibility is income, right? Maybe, if you have more money, you're more kind of arrogant and outgoing as a result, and your parents have more money to put you in more sports. And you can imagine other possibilities too. So those are the three possibilities that you can't know which one is right if this is the only information you have. So the key term third variable problem just means you can't rule this one out. The case where there's some variable you didn't measure that causes both of them. So one thing that you're taught in intro, and that this is right, is that the way to more conclusively show that there's an effect is to do an experiment. But there are other more indirect means of providing evidence of causation. There are many situations in which we just can't do experiments. So I mentioned divorce. If you want to look at the effect of divorce on child development, you can't randomly assign families to the divorce condition and the no divorce condition, right? Now, but that doesn't mean we're helpless. We can still provide some evidence that points at causation. And the way to think about these more indirect methods is to think back to those three criteria. So these are the three criteria for making a causal claim. So covariation, so the two variables, it basically means correlation. The two variables go together, that's step one. Temporal precedence. And ruling out alternative explanations. So this is a review from prior chapter. So you can do these with correlational data to some degree. The one that you can't do decisively is the third one. So one example that there's been a lot of interesting work on is the correlation between inequality in a society, like income inequality, and life expectancy. More inequality means shorter life expectancy. So now that's just a correlation. That only establishes one. More inequality means shorter lives on average in a society. Now, people may ask, is this causal? Does having a more unequal society affect life expectancy? So for two, you can't do an experiment, obviously. We're not going to randomly assign countries to the more or less equal conditions. But you can look at historical data and ask, do changes in inequality come before changes in life expectancy? And if it does, that's another step. And then step three would be, you can look for variables that are correlated with both. So for example, some of the more equal countries, places like Scandinavia, have more ethnic homogeneity, so like less diversity, I guess would be the term. So you could ask, is that, if we control for that statistically, does the relationship stay here? Is there still a relationship even if you control for an alternative variable? For whatever it's worth, the relationship does stay after controlling for variables like that. Now, you're still not home free. It's still not as conclusive as doing an experiment. That's the most decisive way to rule out alternative explanations. But there are statistical ways of doing that that at least point in the direction of the relationship being causal. I had had a video to show about that last point about the inequality example. I'll just say there's Richard Wilkinson is the scholar who does work on this. It's kind of interesting. He wrote a paper with his partner, really helpfully going through how to do these kinds of things in cases where you can't do an experiment. One thing I will say from that paper that's interesting, he adds another criterion that is not testable, which is some kind of mechanism, right? If you know, based on other research, that there's a mechanism that can make it so that this causes this, that's helpful. So think, for example, about climate change. That's another case where we're not going to do an experiment. There's a correlation between carbon dioxide levels and temperature. But we also know there's a mechanism by which CO2 can affect temperature. CO2 is a greenhouse gas, right? It traps heat. So the fact that we know there is such a mechanism is another way of providing evidence that there's a causal relationship. Yeah, okay, I think we can still finish. So that's all I have to say about correlational type data. Any questions?
There's a key term, direction of cause and effect.
Good, so direction of cause and effect, so those three possibilities, that's basically a way of saying you don't know if it's one or two. You don't know which way the arrow goes, basically.
You don't know if it's A or B.
Yeah, you don't know which one's the cause and which one's the effect. Okay, so with experiments, and this is of course review, you have your independent variable and your dependent variable. So in the sports case, you get a sample and you randomly assign people to two conditions. One group plays 5 sports, the other plays 1 sport. So this is the variable you manipulate or control, the independent variable. The variable you measure at the end is the dependent variable, which we'll say is extroversion. You'll measure it in both conditions. Does anyone remember the common way of remembering which one is which? So this is a gift, I guess, because these are very important terms in psych. The way to think about it is, what's your hypothesis? Your hypothesis is that the independent variable causes a change in the dependent variable. So sports leads to more extroversion. If your hypothesis is right, the dependent variable depends on the independent variable, right? If one thing causes the second thing, that means the second thing depends on the first thing, right? So that's a little trick to make sure you remember which is which. So the most important ingredient in an experiment is this one, random assignment. That's what takes care of criterion 3, the ruling out of alternative explanations. What random assignment is supposed to do is make sure that these two groups are basically the same for the other variables that might be relevant. So you're, at least hopefully, getting rid of confounding variables. Although, as one question pointed at, they won't be exactly the same. There still will be some differences between the two groups. So there you hope that replication takes care of that. If the pattern stays the same and you do this many times and you're not p-hacking, then you can be more confident that there is a causal relationship between the IV and the DV. Okay, so another term you have to know here, and we're close to the end. And once we finish, I will say a few things about the survey, just because I got some questions during the break that made me think I should say a few things to make sure we don't have some issues on day-to-day. So a term that relates to experiments is internal validity, which you would have seen in intro psych. Let me just review it. So you hope that your experiment or your study that you claim is an experiment provides evidence that the independent variable caused a change in the dependent variable. Internal validity is how confident are you that this arrow is there? That's one way of saying it. How confident are you that the independent variable caused a change in the dependent variable? How confident are you that the independent variable caused a change in the dependent variable? And it's called internal because it means how confident are you that that happened within your study? So it's not about whether that result will generalize to the real world. That's external validity, which we talk about later. It's just within your sample or within your study, how confident are you that this is what happened? And the main threat to internal validity is confounding variables or confounds, which we talked about earlier, right? Anything that's different between the two conditions that isn't the independent variable, that's going to be a threat to internal validity. So think of my Edmonton and Vancouver example, right? So the independent variable there is my teaching method, but there's something else that was different between the two cases, right? The city. So I don't know if my teaching method is what made the Edmonton kids do better. So therefore it has low internal validity. Any questions on this? Yep.
Is there a good way to measure that or quantify it?
A way to picture it?
Just quantify it.
Oh, quantify it. None that you'll have to know for the test. None that jumps into my mind. Maybe there is. So just a few more terms. Some special types of experiments, one of which isn't technically an experiment, but if it's the right kind, it can allow you to make similar inferences. So most of the experiments we talk about in psychology are lab experiments, but there are also field experiments. So that means they're done out in the real world. So one funny example that was missing one ingredient, but it's easy to imagine something that would count as a field experiment in this sense. This is, in my opinion, the funniest study ever done in psychology. If you're in my intro class, you would have heard about this. They sent out a group of attractive men and attractive women, some of you have heard of this, into the real world, I think just into a university campus. And they told them to approach random strangers of the opposite sex and say, hello, my name is so-and-so, I find you very attractive. Would you like to? And they would ask one of three questions. Now, they didn't randomly assign people to the three conditions, but if they had, it would be a field experiment. This, another funny thing for the day, the three questions were, will you go to dinner with me tonight? Will you go back to my apartment? And will you go to bed with me? And so when women were approached by random good-looking men of the opposites, random good-looking men, 50% say yes to dinner. Less than 10% say yes to the apartment, and not a single person in the study said yes to the final request. Whereas the men, again, 50% say yes to dinner, so they're equal levels of choosiness. Over 60% said yes to the apartment, and 75% say yes to the last one. So one of the funniest and kind of most depressing studies in psychology. So if this had been randomly assigned, like they had a random number generator and let it pick which thing they asked, then this would count as a field experiment.
There are not ethical considerations for these things?
It was done in the 80s, so,
Okay.
some of the stuff was still just starting to be implemented. It might be tough to get away with today. Yes.
They're just asking questions. They're not actually getting them to do it.
Yeah, but what
No.
about when I say yes to go to bed and she's like, just kidding.
Oh, that's such a manners problem. That's the real ethical problem here.
That's the issue here.
The disappointment.
It creates like safety concerns.
Oh, no. Okay, anyways, I should probably move on before I get in trouble. Okay, so the other type, something called a natural experiment. The idea here is people are assigned to the conditions by nature in ways that resemble or at least approach randomization. So you can have cases where people are in two conditions in a way that's at least somewhat random. One example is twin studies. So, and I'm not talking about the twins reared apart studies. I mean cases that compare the similarity of we'll just say identical. The similarity of identical twins with the similarity of fraternal twins. So you look at people who share 100% of their DNA and people who share half of their DNA. And we're not talking about adoption, we're talking about people who also share the home environment. And the idea here is whether you are an identical or a fraternal twin is sort of random. It's chosen by nature, it just happens in utero. And so you can then, with more confidence, infer that the effect of the extra genes is causal. The effect of the extra shared genes. So that's an example of a natural experiment.
Would it specifically be of the same gender then? Otherwise there's...
Yeah, typically these studies will make sure it's, so identical twins are always same sex. But fraternal, they look at, same sex fraternal twins. Good question. Okay, the last term is just ethical and practical considerations with experiments, which I've already basically talked about this. Just the fact that there are some types of experiments that would be nice because they'd allow us to make causal inferences, but you just can't do, right? Think of my divorce case. You can't randomly assign people to the divorce condition and the stay together condition. Okay, so I was gonna show a video of David Deutsch talking about how to form hypotheses and how to think about them, since data day is next week. But you know what? A, we don't have much time, and B, a lot of you seem very stressed about picking an idea. Let me just say, if you're stressed and don't have a good idea, just do something easy. As I've already said, I'm not expecting you guys to, in this window of time, have a brilliant, groundbreaking hypothesis. This class is not really about that. It's more about showing you the steps. So if you still don't have an idea for the survey, as I say, it's due next week, so just think of something easy and implement it in your survey. Now, I want to be clear because some people have asked me about this. The key issue that some people have, the samples I've been shown have all had the same problem, which is the independent variable has to involve random assignment to 2 conditions. It can't be a question you ask with 2 answers. So it has to look like this. And the randomization is already built into my template. You just have to edit the 2 conditions and put in whatever thing you're going to put in. So it has to be that the 30 of your classmates will get randomly assigned to 2 conditions. So remember, in my example, I think it was comedy and horror. So in one condition, you're told, think about and write about your favorite comedy for a little bit. In this condition, think about a horror movie for a minute. So that's the independent variable, right? The thing that you're manipulating or controlling. And then you need 2 dependent variables. And if you're lazy, you can just make them 2 questions. I don't really care. So in my case, it was happiness and extroversion. So then next week, everyone will do all the surveys, and we'll measure, is there a correlation between these 2, and are people's scores on these 2 DVs different depending on which condition they're in. So that's the key thing to be ready for. I'd also encourage you to do a few trial runs of your experiment to make sure it works, because little things can go wrong. That'll make things easier next week. So yeah, and that's 5% of your grade. Next week there's a participation activity to make sure you did it. So yeah, any final questions? So I don't believe there's a class after here. You're welcome to stick around. I can stay a bit late. If you want to play with Qualtrics here before next week, that's totally fine. So you're free to go or stay. See you all next week for data.